a method which is very popular in the controls community to prove stability. Stability is a topic which is sort of people in control obsess over it, because when you have a controller, a torque profile, you want to be certain that that profile actually is able to stabilize the system. Okay, what stability means here is reaching some kind of a zero. The zero is usually the errors in position or orientation. Okay, so what Lyapunov's direct method does is it basically tries to come up with a potential function v of x. So note that v is only a function of x, x being the state. It's not a function of time. And we want to ensure that this energy-like function decreases over time. Then if you can find such a function, then you can be certain that the system is stable. Okay, so energy-like function. So think of a pendulum. If you have a pendulum, and then you let it go from a non-zero position, it'll obviously come back to, if there's damping, it'll obviously come back to the vertically downward position. So that is basically the sort of the position where we want to try to control over. And if you can find v of x such that that energy-like function is dissipated, that is, the energy goes away, then you basically proved that pendulum is stable over the vertically downward position. So for this case, you'll see that you can actually use the energy of the pendulum as a proxy for v, and then you can show that it's stable. Now it's sort of intuitive for single link pendulum. If you have a more complex system, finding v of x is not that trivial. Okay, and that's where there are people who come up with methods to figure out v of x. Okay, now here is some definitions. So consider the system x dot equals f of x. Okay, so there is no control here. U is not there. U is the control, or torque is the control. With equilibrium position x dot equals 0. So that's the equilibrium. That is when the velocity or rate of change of x is 0. X could actually be position velocity. So in this case, rate of change of position, which is velocity, or rate of change of velocity, which is acceleration, is 0. At x equals 0 means that f of 0 is 0, right? Now, if we can find the Lyapunov function v of x such that there are two conditions need to be met. One condition is that v of x is always positive. Energy cannot be negative in this sense. So it's the mathematical way of saying this, it's positive definite. And you say it's positive definite is because v of x, usually when you look at v of x, and you look at the eigenvalues, those eigenvalues should be positive of the form of v of x. And I'll get to that in just a bit. Why vx is scalar, by the way, but inside v of x, there is a positive definite matrix, and that's why it should be positive definite. I'll come to that in just a bit. The rate of change of v dot x is, by chain rule, is this. So you can see that you can write it as dv dx dx dt, but dx dt is f of x. And this v dot x, which is the rate of change of x with respect to time, should be negative definite, or it should be less than 0. In that case, x0 is considered stable. Okay. Then this is just saying that what is asymptotically stable. When something is asymptotically stable, this is what is asymptotically stable. It sort of goes to 0, but never really goes to 0 at infinite time. It takes infinite time to go to 0. For most cases, going close to 0 is acceptable, and they are fine with that. So that is the asymptotically stable. And the only difference between this, so this, by the way, these two steps are illustrated in this graph, where it actually goes to 0 in finite time. And here you can see it does not go to 0, but never reaches 0. And that is only the only change in the condition is right here. If you see this, this is less than 0. It is not less than equal to 0. So it never reaches 0, but it's less than 0. So you can never be sure it reaches 0, which means x then never reaches 0. So that's the asymptotically stable condition. Okay, so here is an example which illustrates this idea. Okay, a spring mass damper, spring constant K, damping C, mass M. X is the displacement from the 0 position. So typically what you do is for this pendulum spring mass damper, you pull it to the right, let it go, and when you let it go, it goes back and forth. If the C, if this damping is greater than 0, you know that it actually goes to 0. It actually goes to 0 in finite time. It's asymptotically stable. So the equilibrium point is x equals 0. That at this point, the system will come to rest. And that's intuitively clear to us, right? Because of damping is greater than 0. So how is this analyzed using Lyapunov function? Well, first we'll choose the Lyapunov function to be the energy. Okay, so there is a half mv square, half kx square, spring energy and energy stored in the mass. We know that v of x is greater than 0. Okay, now v of x is greater than 0 is because assume x and x dot is not 0, it's not at the equilibrium, then v of x is clearly positive, and that's very important. It's the first condition. So we start off assuming this condition, which is condition 1 from the previous page. And then we have to now somehow show that v dot x is less than 0. So how we do that? We will take the derivative of v of x. So derivative of this term gives you mx x double dot. This will be chain rule again. Half kx square kx x dot. Move x dot out. But this mx double dot plus kx mx double dot plus kx is minus cx dot, right? Where did I get this from? It's from this equation. So I just moved this cx dot on the right side. So when I move that, I get cx dot square is what v dot x is. Okay, now clearly c is greater than 0, and x dot can be, well, let's say it's some positive value. V dot x is clearly decreasing since c is greater than 0. And as long as x dot not equal to. So we know that we found the v of x, which we assumed, actually satisfied the second condition. And the second condition is that v dot x is less than equal to 0. Okay, it is 0 when x dot equals 0. So when x dot equals 0, it's 0, but otherwise it's less than 0. So it is decreasing. There is, however, a problem with this. So we have shown that v dot x is minus cx dot square, right? Now this is clearly less than 0 or equal to 0. Okay, it is actually 0 when x dot equal to 0, but it may be equal to 0 when x is not equal to 0. That is, what if there's another equilibrium for this mass spring system? So this is x equals 0. What if there was another position, x not equal to 0, where x dot equal to 0, right? It could be sitting with a 0 speed at a non-zero x position. So that does not prove that it is stable. So for this, is not proven. There's something called Lassalle's invariance, which states that if x dot equals f of x with a Lyapunov function v of x and v dot x 0, the same conditions which we saw for this example. If x equals 0 is equilibrium, is the lone point such that vx equals 0, then x equal to 0 is asymptotically stable. So that is, best way to illustrate that is through this example. Now we've shown that v dot x is minus cx square equal to 0 at x dot equals 0. What remains to be shown is that we only get this at x equals 0 and no other x. If we can show that this is true only at x equals 0, then it proves that the system is stable. So that is basically Lassalle's invariance. And to show that, what you need to do is you need to take the equations and you just have to take the, well, let's see. So we take the equations. This is mx double dot cx dot plus kx equals 0. We put x double dot equal to 0, right? Because if x dot equals 0, then x double dot will be equal to 0, just to take derivative. This is x dot equal to 0. And then what we find is that only happens when x equals 0. So we've shown that when x dot equals 0, x equals 0. So x equals 0 is the lone point at such that v dot x equals 0, and hence x0 is asymptotically stable. Okay, so you just have to prove this. That's the whole crux of. Okay, so that's the Salle invariance. Now let's get back to the the what do you call, the pendulum example. Okay, just generic example, and we can do a lot of good, nice things with this whole idea of using Lyapunov function. So let's take the proportional derivative control, okay, which is simply kpq minus kdq dot. And here, we just assuming that we want to have the equilibrium position is q equals 0. Okay, now this can be changed to any other position by just defining, instead of q, we define the error. So equilibrium in this case is q equals 0. Okay, if you want to change it to a reference, if there was a reference, let's say qr, which is not equal to 0, then you just replace this with E, which is q minus qr, and then this will change to E dot, and then you can just do the same thing, prove the same thing for E equals 0, which is q equals qr. Okay, but this is sort of very generalizable. Just take it as kpq minus kdq dot. Now we'll consider two cases. The first case is when there's no gravity. So here is the equation with g of q equal to 0. No gravity is g of q equal to 0. Okay, so let's say that the manipulator is in the horizontal plane. If it's in the horizontal plane, then there's no gravity, assuming it's a planar manipulator, of course. So this is the equation. I just substitute the value for torque. This is the simple proportional derivative controller. Okay, so then the Lyapunov function, we do the same thing. We assume it to be the potential energy, and then the kinetic energy. We take the derivative with respect to time. Okay, so this is just a mathematical manipulation. Here we'll have to use the chain rule because there are two things, both are functions of time. There's mass matrix and then there's q. So taking the derivative, there are two terms which will pop up here. Okay, now q dot transpose q dot, that's actually the same thing. There are three terms, but really there are two terms, because q dot and q dot, when you take the derivative twice, you'll get 2 times that, and so that half will cancel off. So there'll no half when one of these terms. This doesn't look right to me. It should be, yeah, this is right. So this just takes the derivative of this, and then you can do that one, and then half disappears because there's two terms involving q dot, and then this is this term, which is basically taking the derivative of m dot, and then here because you have again two terms here, q and q dot, you take that twice, and that's why there's been no half here. It'll disappear, and then kp is a constant. Anyway, so once you do this, you can club this as 0.5 m dot q dot minus cq minus kdq dot. Now it does happen that can be shown that, and I will not do this here. You need Christoffel symbol and do the manipulation. It can be shown that term, this term which I put here from m dot q dot minus cq q dot, this term, these two terms, can be shown that it is skew-symmetric matrix. Okay, remember, skew-symmetric matrix has 0, 0, 0 minus omega, I put minus AZ, AY, be 0, 0, 0 minus AZ, AY minus AX, AZ minus AY, AX, something like this. This is a skew symmetric matrix. Now this, once you show that skew symmetric matrix, it actually drops off from there. So when you take this multiplication, if you just assume this form actually, and then you just do the simplification, it actually drops off because there are some terms which will be on the top diagonal, the top part of the diagonal will give you positive terms, on the bottom will give negative of the top term when you do that multiplication, and then that drops off. So what you're left with is just, is that here? You're left with here is these two parts cancel with each other. They are equal to 0. And you only left with this last term, which I wrote down here. So V dot Q is Q dot transpose KD Q dot being the velocity. Okay, now again, you'll see that you'll end up with the same issue, which is even though V of Q is positive, so V of Q meets the first condition, it's positive, and then V dot Q is less than 0, we have to be very certain that Q dot 0 is alone, Q dot equals 0 only at Q equals 0, but there's a possibility that Q dot is not 0 at Q equals 0. So that is the 0 position is not the equilibrium position, but something else. So now again, we invoke the Lasser's invariance. What we do here is if Q dot is 0, okay, because you want to see what's the consequence of this assumption, Q double dot is 0. This is the equation of motion where I put the torque and move things around. I just put Q dot 0, and you're left with this term equal to 0, which means Q equals 0. This is basically using the same logic as before, which shows that V dot Q equals 0 at Q equals 0. So a PD controller leads to asymptotic stability for, the important thing is no gravity. Okay, we only shown this when gravity was 0. There was no gravity in the equations. Now, what happens if there's gravity? So now gravity is not equal to 0. We have actually actively put gravity. Okay, if you put a PD controller, and I think this is kind of interesting, is that when you actually put, so this is the equation of the manipulator. We put torque equals this value, PD controller. We move this here. Now, when the system reaches a steady state, what is the steady state? Steady state is when the velocity in the acceleration is 0. So if you put Q double dot equal to 0, put this 0, this term will be 0. This term will be 0. So you're only left with G of Q, right? Because Q is not 0. It's some equilibrium position. That's the term here. And then the other term, which will not be 0, is KPQ. So you see that when you have gravity and you assume a PD controller, you will get Q equals, Q is not 0. Because Q is basically this thing here, minus G of Q, KPQ is minus G of Q. Now you cannot quite take KP on the other side unless KP is a diagonal matrix. If KP is a diagonal matrix, yeah, you can take the inverse of KP, but you see that there's always going to be a steady state error. Steady state. So the pendulum will never be at 0 position. It will be off 0 position because of gravity. So if you keep increasing Kp, you will keep decreasing Q because this product should be minus G of Q. But no matter how big you make Kp, there'll always be a steady state error. That's the thing. So high gains will not get you close to 0. It'll get you very close to 0, but not equal to 0. So Kp to a large value, but Q can never be equal to 0 because of this issue. So how do you fix that? a PD controller cannot achieve steady state error equal to 0. So this is like, now we have shown this like a proof that a PD controller cannot achieve steady state error equal to 0. So if you just do PD controller, you'll never achieve 0. However, it can be fixed in two ways. One is adding gravity compensation. So I'll show you what that is, and then adding integral control. Okay, so we've not seen both of these. Well, we've seen the gravity control, we've not seen integral control. Okay, so what gravity compensation does is you basically assume this form. So this is a PD controller already there, and you just add a small term to it. This is just the gravity term. Okay, it's nothing as fancy as this controller here. You can see this controller has, it has gravity, it has C, it has all these things. This is even simpler than that. It just has G, Kp, and Kd. Okay, now we can actually show that this controller works. Just a simple addition of gravity. So if you take the equations of motion, which is this, I put in the value for torque. So torque is G of Q minus KPQ minus KDQ dot. Here, nice, the G's cancels off. You're left with MQ double dot CQ, KP, KD. So that's your new equation. Now, when steady state is reached, Q dot is 0. So the pendulum is at a 0 velocity. That's steady state. Q double dot equals 0. Acceleration is 0. That's just taking the derivative of Q dot. If you put that, you will see that this is 0. This will be 0. And this is 0. So we get essentially KPQ equals 0. So only this term remains, and that is precisely given here. KPQ equals 0, which implies Q is 0. So a simple controller which does gravity compensation is good enough. You don't really need to do all that mass matrix, and that's really good news, because all you need to worry now is to just compute G of Q, and that computation is fairly straightforward. We've seen recursive Newton-Euler. That's the easier one. The harder one is the mass matrix. So the other way to fix this issue is the proportional integral derivative control. This is the form of a proportional integral derivative control. Okay, here we have KPQ minus KDQ dot, the proportional derivative term, and then there is this third term, which is the integral control. It basically takes QDT, it sums the joint angles, and then just multiplies with the gain matrix Ki, and then subtracts it. Okay, now if you substitute this in the same equation, this is the equation of motion, left hand side. Here's the torque. If you put Q dot equal to 0, so let's put Q dot equal to 0. Well, you'll see that if you put Q dot 0, then Q double dot 0, that's the steady state. So here, this term will be 0, this term will be 0, this term is not 0, this term will be 0. And so you're left with KPQ plus KI Q dt equals minus G of Q. So this term remains, this term remains, and this term remains. So those terms are written here. Okay, now the part is you have to analyze this particular equation. So we take the derivative with respect to time. So when you take the derivative, it becomes Kp times Q dot, and the derivative of integral is just Q. So derivative of Q dot dt is Q equals G of Q, but G of Q is, it's going to be, actually I should have written this down, it should be something like GQ Q dot it'll be dg dq Q dot. This is by the chain rule, right? So this is basically going to be 0, because Q dot is 0, Q dot is 0, Q dot is 0. And so we can show that the only term remains is this, which is equal to 0, and implies Q is 0. So this is just another way in which you can get correction of steady state error, which is the proportional integral derivative control. So two ways to get 0 steady state error in PID, and gravity. Of course, there are other ways, inverse dynamics, but these will do. Okay, here is the grand summary of everything we've talked about. Okay, so the manipulator equations are given first, mq cq q dot plus g of q, and these are just recommendations of how to go about designing a controller. If you want to do a proportional derivative control, that would be kp q minus qr kd q dot minus q dot r dot. Okay, you want to use this only for, and this is just the recommendation, where this everything is moving slow, okay, because it doesn't really take into account the acceleration, and there's no gravity, so it's in the horizontal plane. Okay, the second controller is gravity plus PD. So in this case, what you do is you have the gravity term, and then you do proportional derivative control. Okay, now sometimes, as we've talked about before, this requires sensor measurement. So here is the sensor measurement. Q is a sensor which is mounted on the manipulator. It could be, it's usually an encoder. An encoder measures the position. So that position is going to be delayed because of your control system. Then you just replace G of Q with G of QR, where QR is the reference, and the reference is something which you compute offline or online, but that's known, so you don't have to rely on sensors. Okay, so there's actually two controllers sitting here. One is with sensor feedback from G and no sensor feedback. Okay, third one is proportional integral derivative control. Here you just do kp q minus qr kd q dot minus q dot r minus ki summation. Here I wrote the discrete form of the equation. There's no dt because you're just summing q minus qr, but it's over time. Okay, so this is used when you are not sure what mcg is, because you can see that mass, Coriolis term, gravity does not appear in that equation. They are uncertain or unknown. So the I term, as we've noted, helps to cancel out constant disturbance. So G of Q, it cancels out. But if you have another disturbance, say external disturbance, let's say there is an added mass to the manipulator, that will be taken care of by the integral term. Okay, then number 4, inverse dynamics. This gets slightly more sophisticated now because you're going to use more feedback. So here what happens is this is one of the first ones we discussed. There's G of Q, C, M, and then there is, of course, the sort of the PD part. Now, this is only useful when you have an accurate model, that is, you know, M, C, G. When the sensors are less noisy, which means that Q, you have a very good estimate of Q, and there's no delay. So Q estimate is good and no delay. Now, if you don't have, if none of these are satisfied, 1, 2, and 3, then what you want to do is you want to instead use a feed-forward, feedback controller. What it does here is essentially changes this G of term with Q of R, CQ QR dot M of QR. And that way, you still need an accurate model, but you can live with noisy sensors to some extent. Remember, you're still feeding Q. You still need sensors. You can't escape them. But because you're not using this C and M, and C actually contains Q square, Q dot square, not Q square, but Q dot square. So if you have velocity squared and velocity is noisy and you're squaring noise, it's going to give you a really jittery control. And that's why you really don't want to use noisy sensors when you have C. The delay, there's other issues with delay, but delay actually can cause it to be a feed forward instead of feedback. Feedback is stable. Feed forward is not. Feed forward control in the traditional sense is not stable. This feed forward is just feeding this in the forward loop, which is basically different from feed feedback, what's the term? It's feedback is when you take the negative of the signal and feed it back, and feed, I'm banking on the term, it's feed forward, no, it's feed, it's actually called positive feedback. So usually when you feed back Q, you're feeding the negative of Q, and that's stable. The positive feedback is when you actually feed back not minus Q, but positive Q. That happens when you have a delay. A feedback can become positive feedback, and that can make the system unstable. And then, of course, you want to use this when time delay is just talked about. Okay, so those are the 5 controllers which we talked about, and I showed you the rationale behind tuning KP-KD based on damping, right? And then the reason for having gravity and PID is to cancel off the steady state error, and I also showed you Lyapunov function.